All right, you guys have about 5 minutes to go through these problems, and then we will get started for the day. All right, so most of these we're going to be doing some sort of replacement. Pretty much usually just replacing our CL with whatever's attacking. So in this first one we have amide, which means, or sorry, an amine, which is going to replace our CL to form an amide. We have two different groups on there. We have a methyl, we have an ethyl. This bond's freely rotatable, so you could draw it as with the ethyl up and the methyl down if you wanted to. It's all the same thing. Okay. I didn't really talk too much about when you have different for these anhydrides. So on the right, we have basically ethanoic acid and propanoic acid. So there's two different things that can happen. Your methanol can either attack this carbonyl, which would give you methanol, or sorry, the ester of that, versus attacking at this position, which would give you a different ester. So if we do the one that is in looks like red, we are going to form this methyl ester versus the one in blue, which will give us the propyl version of that. All right, so water in pyridine is going to give us a carboxylic acid back. This LiAlOR3H is our, the question in the chat. Oh, yeah, so for these anhydrides, you don't need pyridine for them because there's no proton to pull off when you do the attack. Normally, when you do attack on, well, I guess you do. Yeah, never mind, you need pyridine for these. It'll still work. You might as well just make them the same. So let's add pyridine for this one. I think your book doesn't list them, but they do go faster if you add it. Okay, so this is our hindered reducing agent. If I throw this in, it's going to reduce it selectively down to just our aldehyde. We have our hindered alkylating reagent. It's got this propyl group here, so we're adding propyls to this compound, getting rid of the Cl. This is our selective one. It's going to give us just the ketone versus a Grignard, which is going to be our pretty heavy alkylating reagent. This is going to end up alkylating twice. To give us our alcohol here. Okay, on April 16th and 19th, I'll put a message on Canvas, but these will only be over Zoom for those days. So for most of you, that's the norm, but for the people who are actually in person, you guys are gonna have to sit in front of your computer for that one. Okay, so today I'm gonna talk through a bunch of different mechanisms. We're gonna finish up chapter 20, which is pretty mechanism heavy. They're all kind of similar mechanisms for the most part. So if you're looking in your book, this is mechanism 20.6. Which is referred to as the Fischer esterification. So typically to make an ester from a carboxylic acid, you would take SSCl2 to make the acid chloride. You could throw in methanol and pyridine. To make our acid. There is a simpler way to do this where we can just take our carboxylic acid, throw in methanol and H+, and through about a 7-step process, this can transform into this ester also. So the way this is going to work is we're going to start with, it's somewhat similar to what we're doing with making like acetals and imines. Start with this carboxylic acid. We have H+, so we're going to pick that up on our carbonyl, just like we would with a ketone or an aldehyde. We can have methanol come in and do an attack. We're going to lose this proton off of our methanol. Pick it up on one of our oxygens. Kick out water. Lose that last proton. And we're able to make an ester from this. All these steps are reversible. It's kind of all focused around this step here where our water is attacking this H. There's no reason why this water couldn't attack this H. And more importantly, there's no reason why this methanol couldn't attack this H. So if the methanol attacked, we're just kind of going in the back direction then. And you're going to lead to no product in that case. So for these and most of the reactions today, these arrows are going to go in both directions. Okay, so as we kind of just discussed, you can do this in the opposite direction. So this is mechanism 20.8. It's going to be acid catalyzed. Hydrolysis of esters. So we can also take an ester, throw an H+ in water, and have this go the other direction. So this mechanism, which is fairly identical to the last one we just covered, was going the opposite direction. We're going to take this ester, throw in an H+. We can pick this up on our carbonyl. Water can do an attack. Lose a proton. Pick up that proton on our ester oxygen. Kick out that O- or that O+ here. Make a protonated carboxylic acid. Which can lose that proton to make your regular carboxylic acid. Like the last one, these are all going to be reversible steps. Arrows moving in the direction. Which makes sense because we're basically doing the exact same, the opposite reaction of what we just did. All right, so we learned that if we can take our carboxylic acid, throw in H+ and ethanol, this will allow us to create a methyl ester. We want to reverse this, we can take H+ and water, and get right back to where we started. All right, so an amide is going to work somewhat similar in one direction, but not so much in the other. So we can do a very similar thing to what we just did. This is mechanism 20.11. So this is acid catalyzed hydrolysis of an amide instead of as an ester. It's the exact same concept. You take, instead of an ester, taking an amide, putting in H plus and water will allow us to get to a carboxylic acid. I'm gonna run through this mechanism pretty quickly. Your steps are exactly the same as the last two ones. So H plus, you can pick that up. Protonate. Our water could attack. Lose a proton. Gain the proton back on your amine. H3 plus. No. SpNOH still. Now we can kick this out. Oh, that shouldn't be there. Lose the proton from our carboxylic acid. To get our final product. So these are the exact same steps as before. The only difference is that I'm going to say that not all of your step in this is reversible. So the attack of the amide is really unlikely to happen in this direction. So although most of these steps are reversible, this last one here, or second to last one, is not going to happen in the solution. I'll talk about that for in a second. Someone asked if you need to mention the H3O plus as a byproduct. I mean, you can if you want to, but it's not really necessary for the reaction. No one's doing this to just make NH3. Okay, so like we talked about previously,
Do you mind?
if we take a carboxylic acid, throw in H plus and MEOH, we can make an ester. Throwing in H plus and water, let's go back to the carboxylic acid. Unlike amides, if we try to do this same concept, it's not going to work. So taking a carboxylic acid and throwing in H plus and NH3 is going to end up leading to no reaction. In order to get the amide, we're going to have to go through our SOCl2 pathway. Then add in our amide. To get here. On the other hand, we can just throw in H plus and water. And this will let us go backwards. So this back half of our pathway that we're able to do with esters is going to still apply, but the front half, we're going to have to go through that SOCl2, which is why we talked about it so much. Okay, I'm going to talk about nitriles for a little bit, and then that will actually be the end of the chapter. So let's get started with some nitriles. There are two main ways to make them. The first one is just through like an SN2. So taking haloalkane, throwing in KCN, and acetonitrile. Can let you make one. This also adds the carbon. The other way we can make one is through an amide. So taking an amide, if you throw in a reagent we've seen a lot, which is SOCl2, this is actually going to let you make nitrile. Let me look up the number real quick. This is dehydration of amides. This is mechanism 20.13. So it's going to work somewhat similar to your normal SOCl2 mechanism. We're going to have an amide with SOCl2 in solution. Our nitrogen is going to come and form a double bond. The double bond from the oxygen is going to go to attack the sulfur. Pick up our other double bond to an oxygen. We're going to make a complex. We can kick out one of these CLs by reforming our carbonyl to the sulfur. Yes, sulfonyl, not carbonyl. And then from here, We can have one of the Cl we just kicked out. Pull off one of these protons. We're going to generate a protonated nitrile along with SO2 and Cl minus. Should still have an H on it. That Cl minus can grab this H. And give us a nitrile. All right, so the last mechanism we'll talk about is mechanism 20.14. And I'm only going to do half of it. The book also only does half of it. We'll talk about why in a second. So we're doing another acid catalyzed hydrolysis of nitrile this time. So that means we're going to be adding an H plus in water. So if I take a nitrile, I add an H plus. I can pick up this proton here. As usual, my water can come in. Make kind of like a backwards amide. We're going to have the double bond to the nitrogen, single bond to the oxygen. We'll do a proton transfer. We'll lose that H off the oxygen. We're going to pick it up on the nitrogen like we normally do. You're going to kind of flip it. So your oxygen is going to form a double bond. This is really just a resonance structure. Lose a proton off of that oxygen. And form an amide. So this is where your book stops. And the reason for that is that right now you are an H plus and H2O. And this is the exact same conditions that we were at in mechanism 20.11. So taking an amide, NH plus and water is going to give us a carboxylic acid. So because of that, if we take a nitrile, NH plus and water, this is going to take us all the way to the carboxylic acid. So stepwise, you're thinking of it as H plus and a nitrile gets me to an amide. And then using that exact same set of reagents is going to push me to the carboxylic acid. But really, this middle one is barely observed. You're really going to just force all the way through to your carboxylic acid. So you can't actually make an amide this way through a nitrile. It's going to go to the carboxylic acid. Give you guys a second to keep writing. All right, so if I take my carboxylic acid and I want to make an amide, I'm going to have to go through an SOCl2 pathway. So if I want to make a nitrile, I'm also going to have to go through that. So starting with our carboxylic acid, we had an SOCl2. We can make our acid chloride. Adding an amine. Let's just make an amide. And then, so if we want to get back from here to our carboxylic acid, we could add an H plus water. We want to go forward to a nitrile. SOCl2 will get us here. And then again, taking the same reagent, H plus H2O, will let us go back to a carboxylic acid. So some of these are kind of reversible, some of them aren't. You're like, amide, you can't make a acid chloride back from it, but you can take it all the way to a carboxylic acid. Your nitrile, you can't get back to an amide or an acid chloride, but you can go all the way to the carboxylic acid and make them that way. The last couple of reactions in this chapter that I'm going to talk about, first one is, they're just reductions. So I'm going to go through them real quick. Carboxylic acid, you can throw an LEH, makes an alcohol. You can do the same thing with an amide. You're going to reduce off your carbonyl. And be left with an amine. And you can also do this with a nitrile. You reduce off your triple bond. And also form an amine. So these are two ways to form an amine. Both of them just involve both of them are just LEH doing a reduction, get rid of some amount of double bonds to give you that product. All right, I am going to stop here. On Wednesday, we'll do some synthesis. Friday, we'll do some NMR. And we'll be done with chapter 20 at that point. So I will see you guys on Wednesday.